we install and upgrade these library TensorFlows and these libraries. Uh, then we install scikit optimized library. So this is a code for classification problem. We use MNST dataset and we use four machine learning algorithms. One is random forest support vector machine, k nearest neighbor, artificial neural network. So, and for hyperparameter tuning, we use these four algorithms. One is grid search, another is random search, and last two are based on Bayesian optimization. One is with a Gaussian process, one is with a TPE, tree structured present estimator. So first of all, we import some required libraries. So we import NumPy and Pandas for data handling, and we import visualization libraries, Seaborn and Matplotlib. Then we use this scipy.states to statistical analysis. Then we import dataset from sklearn. It contains a pre-stored dataset. And then we import cross-val score for model evaluation from sklearn.model selection. Then we import these machine learning libraries, random forest classifier, k-neighbor classifiers, and SVC from their respective sklearn libraries. And then we import these matrices. Okay, so first, what is MNST dataset? MNST dataset is a largest database of handwritten digits that is commonly used by the people who want to try techniques and pattern recognition method on real-world data while spending minimal efforts and efforts on pre-processing and formatting. It contains 60,000 training images and 10,000 testing images. So, and all the images have been size normalized and centered in a fixed size image. So this is these are images from MNST dataset. As you can see, these are all the digits from 0 to 9. And so we have 10 classes, and we want to predict which digit it is. So first we load the dataset X and Y. X is image, Y is their label, dataset dot load digit. So it is pre-stored dataset in dataset library. Uh, so we import, and this is as you can see, these are matrices. So these are nothing but images, but shown in matrix format. So now we use baseline machine learning model. First is random forest. So random forest is assemble learning algorithm which can be used for classification and regression. It operates by constructing multiple decision tree during the training and output the mode of classes for classification and mean of it. So as you can see in this, so as you can see, you have three and it is asking one is saying the class C tree, saying the with output is class A. So as we discussed, it combines single decision tree to reduce operating accuracy. Each tree done by what data. As we discussed, also randomness is in with bootstrap sampling. Each tree analysis is predicted by trees is selected by majority voting. Most predicted by predicted output. It has like high accuracy, robustness. It can handle both numerical and categorical features, etc. This is the code for random forest. So first, a random forest classifier. This is the predefining the library. So we import it from there, and this is dot fit. Dot fit will train random forest on our MNST dataset. So, and RF score will give cross value score. We are
Not
expecting accuracy.
hello,
Yes, ma'am.
hello, Mukesh.
Yes, ma'am. Yeah,
Uh,
yes, ma'am.
your voice was not clear for the past 30 seconds. 30 seconds, I think.
Okay, okay.
Your voice was not clear. So maybe you can repeat this random forest part. Although you have already, I mean, the participants, you have already seen this in the theory part, but just this is a recap of what random forest is. And then, okay. So, uh, yes, please continue.
Okay, okay, okay. Okay. Now it is clear?
Yes, yes, it is clear.
O- Okay. So, as we discussed, random forest is a popular assemble learning tools which use multiple decision tree to predict the output. And for code, we have this random forest classifier which is predefined in library. We import it from there, and we trained on our data, MNST data, dot fit by dot fit is for training. So, and then we extract the random forest score, which is accuracy from this training, and accuracy is 93.48. Okay, next one is support vector machine. Support vector machine is a supervised algorithm which can be used for classification, regression, or even outlier detection. It is particularly suited for binary classification. So how it works? It works by finding the optimal hyperplane that best separates the data into different classes. So as we can see in this figure, if we take H1 as hyperplane, so it can't separate two classes, but H2 does, but with a small margin. We want maximum margin from both the classes. So H3 separates them with maximum margins. So as we discussed in theory lectures, so this is a maximum margin hyperplane and margin for an H1 trained with sample from two classes. This is the example. Now, for code, we import this SVC function for SVM from the library. Data. Next is k nearest neighbor. So k nearest neighbor is a powerful supervised algorithm. It is simple but powerful. It can use for classification and regression. It makes prediction based on the majority classes for classification and average value for regression of the k closest data points in the training set. Okay. So let's have this example. Okay. You have green dot as a test value, and you want to classify it to square or triangle. Triangle is red, square is blue. So you want to classify it into triangles or squares. So if we choose k is equal to 3, let's say we have we use k is equal to 3, so we have this uh, solid line circle, and in this circle 2 points are from triangle and one is from square, so it is we will classify it as triangle. But if we take k is equal to 5, then we get this dashed circle. This means there is 3 points which are squares and two is triangle. So we will classify it to squares. So this is how it works. So also, as you can see in the left figure, given the closed, so we are considering k is equal to 3. So the algorithm seeks the three closest point in the training set uh, and adopt the majority vote to classify it as class red. In the right figure, you can see by iteratively repeating the prediction over the whole feature space, we can predict the decision surface. If we have points position specified, red will impact red and blue. So for this, we have predefined function k neighbors class. Predefined function k, we import it from there, and classify from we fit on our MNST dataset. So similarly, we find the accuracy from cross-value score. So it is 96.27. Next one is artificial neural network. So artificial neural network is a computational model inspired by human brain. It consists of well-cognited and transformative relation. So as you can see, this is the example for an artificial neuron that is interconnected group of nodes inspired by simplification of neuron in a brain. In this figure, each circular node represents an artificial neuron, and an arrow represents a connection from the output of one artificial neuron to the input of other. Okay, so this is another example. So if uh, you have two types of one is starfish images, one is sea urchins, and you want to classify them. So how a model will learn features from there? So starfish is one is shape which is triangle, sorry, star-like shape, and for urchins it will have a round shape. So based on that, this AN learned features, these things we have discussed in theory lectures. So yeah, now comes to code. So first, similarly, we import this library. This source model, source model. This it will help us make the model, and these from layers we import potential. From callbacks we import early stopping, and these things will be imported. So this is based on so we put up the processing the digits. We load the digits data set, MNST data set, and this is the RX. So as we discussed, this model have two hidden layers with 23 neurons. Activation function is railing. For output layer, we use softmax function and SGDA optimizer. So as you can see in this, we have 23 neurons, rail activation function, SGDA. Some means if our model is not improving over the epochs, it will stop. So similarly, this is the ANN model. Now we will apply all the four hyperparameter tuning algorithm on this model, on all of the model. So first is grid search for hyperparameter tuning. So grid search across different values of two hyperparameters. As you can see in this figure, for each hyperparameter, 10 different values are considered. So total of 100 different combinations are evaluated and compared. So as you can see, blue contours indicates region with strong results, whereas red ones shows regions with poor results. So just like that, you have to go from left to right, right to left, and you have to cover all the points. So keep it, it tests all the possible combination of specified hyperparameter values. It performs cross-validation using RobertsNet and help in automated model training. So we import grid search from the sk learn.model selection. First, we imply it on a random forest. So for a random forest, we take three parameters. One is n estimators. We take 10, 20, 30. Maximum depth, max depth, 15, 20, 25, 30, 50. And uh, these Gini or entropy, we use these citations. So first, we random forest classifier, we assign a random state one, and then in grid search, we want to apply it on random forest. So first of all, rf.clf, Then parameter. We predefine the parameter. We want to search only these values. So it will take combination like 10, 15 guinea, 10, 20 guinea, 10, 25 guinea, 10, 30 guinea, 10, 50 guinea. Then it will take 20, 50 guinea. Okay, sorry, 10, 50 entropy, 10, 50, 10, 20 entropy. Like this, it will cover all the possible values. We want to achieve the maximum accuracy. So scoring is accuracy. We can assign other metrics also. Then dot fit, it will fit the model, uh, train the model on the data for each of the values in this grid. So here we have 3 cross 3 grid. Okay. So we get citation as Guinea, max depth at 15, and an estimator as 30, and we get accuracy 93.43. So next is support vector machine. The code is same. Here we want to up, up, optimize two parameters. One is C, we take 1, 10, 20, 50, 100. And another is kernel, which kernel is 190 is using 110 is kernel, or RBF kernel, or sigmoid kernel. So it will make a grid, and grid search. First is model name, then parameter name, then scoring is accuracy. CV is free. So it will give the best value for highest accuracy. Highest accuracy. So this one kernel is RBF, and we achieve highest accuracy 95.93. Next is k-meaner. Over there is one parameter which is a number of neighbors. So it means value of k, you want to take k is equal to 2, 4, 6, 8, you want to. So only one parameter. So we
Hello.
optimize this
Uh,
cell.
Hello.
Yes.
Mukesh, actually, it is a bit not clear. We are getting in comments also. The audio is not clear. Now it is clear, but for the past 1 minute, it was not clear.
Oh, okay.
Is it audible now, participants?
So can I explain support vector machine again? So I think
Uh, yes, you can just revise a bit if you can.
okay.
Thank you. Don't worry, participants. This notebook will be shared with you, and you can run it. So if Mukesh, if you can just share it now itself, all the notebooks, they can simultaneously run it.
Yeah.
Yes. Or I think I will share it. No problem. On the canvas, I can share it. Okay, you can. Okay, you can do this also. You can
Yeah.
give the link here.
Yes. Yes. Uh, so I said the note in the chat.
Yes. Yeah, the chat is showing, but your screen is not visible now.
Yeah, yeah,
Still, there is some voice issue.
uh, now is it clear?
Now also, it's not clear. Uh,
One- Now is it clear, ma'am?
yes, yes, it is clear.
Okay, okay. So I'm sharing again.
Yes. So, participants, he has shared the collab link in the chat. You can access that notebook from the chat and simultaneously try to run it.
So we are discussing. Can I continue?
Yes, please,
Yeah.
you can.
Yes. Yeah. So we are discussing grid search for hyperparameter tuning. We first discussed random forest, then support vector machine. We are optimizing two parameter. One is value of C, another is kernel. So for kernel, there is four option: linear, polynomial, RBF, and sigmoid. For value of C, we take five options: 1, 10, 20, 50, 100. So what it will do? It will take for first iteration, it will take one for C, kernel is linear. Then it will take one for C, kernel is polynomial, like this. Then it will take 10 and linear, 10 and polynomial. So it will cover all the values and give the best accuracy achieved in these values. So by running this code, so this is the function grid search CV. It will take first, it will take model. So which is model is SVM slash SVM CLF. Then SVM parameter, we take these two parameter. Then CV is 3. This is parameter for this grid search CV. And scoring is accuracy. We are optimizing accuracy. So, and dot fit will fit the model for all the values. And we get best accuracy is 95.93. And best value for C is 1. And best kernel is RPF according to grid search. So next is k neighbors. So for k neighbors, we have one parameter which is number of neighbors. So first we take neighbors is 2, 4, 6, 8. You can take another value also, 1, 2, 3, 4, 5, like this also. So this is the k neighbor classifier as we discussed. We import it from library. So grid search function first it will take model name, parameter. CV is equal to 3 is default parameter of grid search CV. You don't have to change. And scoring is accuracy. If you want to check the F1 score, other matrices, you can use that also. So then we fit the model and we get the best accuracy 94.544. Number of neighbors is 4. Next is artificial neural network. I already explained this code. We want to check the parameter. One parameter we are taking is optimizer, whether to choose atom or SGT. We want to check whether to use ReLU activation or 10H activation. For number of neurons, whether to take 16, whether to take 16 or 32 neurons. Also for batch size, which one is best, 16 or 32? And for number of epoch, we want to check which one. Okay, the same code, simple. Grids. This is the ANN which we defined and discussed previously. Then parameter, these are the parameter, then parameter, and we want to check the best accuracy. Same dot fit will train the model. So as you can see, it is trained for every possible values. So it's you can see best parameter for base size we got 16, for epoch we get 50, for model activation we get 10H, for neurons we get 32 neurons, and for optimizer we get ADAM optimizer, and we achieve 94.04 accuracy. So another hyperparameter tuning algorithm is random search. So random search is an efficient alternative to grid search that randomly samples hyperparameter meters combination from a predefined distribution. So, so as you can see in this figure, random search across different combination of values for two hyperparameter parameter. In this example, there are 100 different random choices are evaluated. The green bar shows that more individual value for each hyperparameter are considered compared to the grid search. So in grid search, we are checking all the 100 possible values. But in random
we use selected values. Key features is it select random combination of higher parameter instead of checking all. So it is much faster than grid search. And for this code, we import this randomized search CV from sklearn model selection. This is a predefined function, and these other two library. So first we apply this on random search. Same we discuss the parameter. There are two parameter. One is n estimators. One is max depth. Another is criterion is Gini or entropy. Then same. This is a random classifier. Random state is one. Random state it is the model name RF CLF. So it will take similar. Just change the name of function. It is randomized function. So first is model, then parameter distribution, which is we defined here. Then iteration. Iteration means how many values you want to check from it. How many random values you want to it will take randomly any value from 10 to 100, and it should be integer. And it this for max depth we have this range in 5 to 50. It can take any 50 integer value between 5 to 50. So after fitting it on the MNST data set, we get accuracy 94.32. For criterion, we get entropy. For max depth, we get 17. And estimator, we get 84. We get 84. Next, we apply it on the support vector machine. We take same parameter. We take same parameter. We want to check between between for kernel. We want to check polynomial. Check polynomial to kernels only. So this is the S function for SVM, which is redefined, and this for SVM, we have insert SVM function, parameter distribution, and iteration is 20, and we want to take this to be accuracy. Then we fit this model and print the best accuracy and best parameter value. So for C, we get 19.23, 19 RBF. And accuracy we achieve 95.88%. Next, for k nearest neighbor, we want to check neighbors from 1 to 20. So first similar code for this also. Model name Canon, parameter distribution. This time we are trying only 10 iteration, and we want to check maximum accuracy. So we get number of neighbors is 5 and accuracy is 94.60. Next is artificial neural network. For this, all the code is same. Number of parameter, same parameter as previous. We want base size, so 16 or 32, activation from ReLU and 10H, optimizer from Adam and SGD, number of neuron between 100, 10 to 100, epochs between 30 to 50, and also we had 10 to 55, we had 520. Same, we apply this on this model. First is model name, then parameter. We are applying 10 iterations and accuracy. Accuracy is we want to maximize the accuracy. Then we fit the model and we get best value. For base size is 16, for epoch is 30. Model activation, we got ReLU. I think in grid search we got 10 values are changing. In model activation, model neurons is 92. Model optimizer is Adam. And patience is 15. Next is neurons Bayesian optimization for hyperparameter tuning. So Bayesian optimization smartly spaces and place potential choice of hyperparameter by deciding which combination to explore next based on previous observation. So first is Bayesian optimization with Gaussian process. So Bayesian optimization it uses Gaussian process as surrogate model to approximate the true objective function and an actual. Also, it evaluates the suggested point is evaluated using the true objectives, and these things we discussed in the theory class. So, from SKOpt, we import optimizer, Bayesian search, and these real category and integer. So first we want to apply it on random forest. Same, we want to check an estimators between 10 to 100 and next step between 5 to 50. Criteria 50, Gini, or entropy. Criteria Gini, similar to the function and base CV, and print the value. In this, we get 94.54. So, okay. So for criterion, we get Guinea. Next step is 12 and 76. Next, we it on support vector machine. Support vector machine, same parameter is with taken. We imply this base search and same to same, just you have to change the name of the model. So you get this value of C and RGB, same for K nearest neighbor. So you can understand it by running this. Same to same. Next one is Bayesian optimization with tree structured present estimator. So it is a non-Gaussian Bayesian optimization techniques. It uses TP instead of Gaussian process. It can be implemented by HyperOpt library. So it has two probability distribution. One is for good configurations and another is for all configurations. So okay. So it can suitable for discrete, conditional, and tree structured spaces. So we import this HyperOpt library and these functions we import it from there. First, we want to apply it on random forest. For random forest, for an estimators, we want to check these integer from an estimators. We will give these values, so you can check this R is phase. So for an estimators, we are checking 10 to 100 and 1. It means 10, 11, 12, 13 like this. And this is a 1 to 32 and space is 1 to 1, 2, 3 like this. And for criterion, Gini and entropy. Similar random forest is imported from the library and we imply this function and then we print the value. So as you can see, this is the F minimum, which is the best value for random forest, and we get uh, we are optimizing what we are optimizing accuracy. We are optimizing accuracy. So we get an estimator is 77 and maximum feature is 6. Criterion is 0. 0 means Gini. 1 means entropy. So we make it as array. Same for support vector machine, same code. Just we have different parameter in different form for this. All the other things are same. So we define a parameter between 0 to 50 And for kernels, we make array, polynomial, or RBF. You can choose all the four kernels also. Okay. So this is CV is equal to this function. Hold function is for Bayesian optimization TPE, and we get the best value. Just same code. You just same the grid search. Grid search is random forest by support vector machine, and grid search and random search by this BOT by support vector machine. Next is K nearest neighbor. Neighbor code we want same code, so it is taking uniform value between 1 to 20. The same code is previous, just put the KNN model, K nearest neighbor model. We get value 4 for best number of neighbors, and another is artificial neural network. Same to same code as we discussed. Same to same. Just you define parameter in other way. So we define optimizer as an array which take now we are taking three optimizer random SGD and RMS probe, and we are taking these values. So just same code, nothing new. Just you have to change the function, and you will receive the best possible parameter value for highest accuracy. So this is the hyperparameter uh, tuning for ML classification models. So if you have any doubt, you can ask. Uh,
Any
and
doubt
I
in
say,
yeah, any doubt in executing this notebook or accessing this notebook, you can ask in the chat box. I think due to bad weather, there are technical issues in between. So these are the algorithms from the machine learning illustrating the hyperparameter tuning. So I think we can proceed further. Am I audible? Am I audible? Akash is
yes, yes,
having some doubt. Yes, so
yes.
Akash is having some doubt. Harshit, please make him the panelist so that he can speak. Yes, Akash, please tell us.
Ma'am, screen is not visible as of now.
Mukesh tried
My
to share it
screen.
once again. Actually, we
Okay.
can we can see it, but you can, yeah, you can try it again. From where are you connected, Akash? Are you connecting via the MNIT network?
Yes, ma'am.
Yeah, so now it is like creating a lot of problem because of the bad weather and I don't know what issue. So, is his screen visible now?
No, no, ma'am.
Anyone else facing this problem?
Yeah, it's fine now, ma'am.
Now, yeah, I can also see now. Okay. So we can continue with the convolutional neural
So,
networks.
ma'am, actually, whenever we are trying to use this, so
Mm-hmm.
parameter tuning. So at that time,
can you write it in the chat box because I cannot hear anything? Mukesh, can you hear me?
Yes, ma'am.
You can hear me, but
Yeah, I can hear you.
yes, Akash, if you can
So,
type it in the
may
chat
not
box
we,
because you're not audible.
if my voice is clear, meanwhile,
Yes,
I can explain
your voice
CNN
is clear.
and I will answer in last.
Okay, okay,
Okay.
continue.
So, in this uh, s- notebook, we will discuss CNN models. So we are using some data sets from Kaggle. So to import the data set from Kaggle in Google Colab, use this import Kaggle hub and data set location to it. It will import the data set to Google Colab. So first, we have to import basic library. These libraries similar as I discussed. These are building and running deep learning model. We use this TensorFlow.keras.layers, import different layers, input layer, con2D max pooling layer, convolutional layer, it means max pooling layer, dropout, base normalization, convolutional transpose, concatenate, and also cross function. Being aware how we are processing these images. But in contrast, machine requires instructions, clear instructions, and structured data to understand the visual information. And as we know, all the images are nothing but pixel values for a computer. So by changing or analyzing the pixel value, we can analyze the image. So this is the basic diagram for neural network. So if there is a problem of classifying horse, zebra, and dog, so this is the problem. If we insert the image, we get some layers, their connections, and we perform the classification based on probability. 70% means it is clearly zebra because the rest of two are less. So basic component of CNN is one is input layer, convolutional layer, activation function layer. These we know we discussed in theory lecture. Flattening layer, fully connected, output layer, loss function, optimization. Image is passed through convolutional layer to generate feature map using filters. Then we use some padding strategy. Then we downsample the features map to reduce dimensionality and computation. To reduce dimensional layer, extract more specific feature, more specific and then fully collected means flattens the output to make a single array. And then we did this by forward and backward processing. This is all you know that. So first we want to construct a basic model, simple CNN model for image classification. Let's we have this cipher 10 data set which is 32 cross 3 sizes of image, small images. So we are building this a small model. First is input layer for 32 cross 3 is input. We take 32 filters, kernel size is 3 cross 3, function is ReLU. Another, we use then max pooling layer, convolutional layer. So first we have input is 32 cross 3. Then after applying the convolutional layer, we get this input 30 cross 30. cross 32, 32 filters and 30 cross 30. Then after max pooling, we use pooling of size 2 cross 2. What is max pooling? Pooling is doing with these features. So it is maximizing the feature in the in the we and these cross section we again max pooling filters 3 cross max pooling specify into 10 class. Okay, so so we apply this max pooling layer with filter size 2 cross 2. Then again we apply convolutional layer with ReLU activation function. Then again max pooling. Then flattens the output. Then we apply the dense layer with ReLU activation. And at last we apply dense layer with soft max activation. As we discussed Prinkam's activation function lecture. So if you want to classify into the 10 classes, we need probabilities for 10 classes. Just like that, we apply this soft max function. So model one, we name it model one. So to print summary, so model one dot summary is the function for it. So in this model, we have 1,67,562 parameters. In all of them are trainable. So we are going to train this model. Okay, you can, I make this diagram here, but you can print the diagram of models you defined. So this is the function. You have to import plot model from this library, and so you want to print the model one, so name of model one, then name of the figure. So shapes, you can change the shape, you can change the DPI to increase quality. So this is the same figure. You can print it this like this. Now we have to compile the model. We make the model. Now we have to compile the model. We compile the model means with matrices, with function, with optimizers. So we are taking accuracy. It measures the overall proportion of correct prediction. We use precision. It evaluates how many of the predicted positive level were actually correct. We use recall measures. It measures how many of the actual positive level were correctly identified. And also we use AUC, which is area under curve. It indicates the model's ability to uh, differentiate between classes. So these metrics give us better understanding of how well the model performed, especially in multi-class scenario. So just this is the function model.compile for optimizer is atom. You can choose different optimizers for loss, categorical cross entropy loss for matrices. We are using accuracy, precision, recall, AUC. Then we need a data set to train a model. So we load the data set Cipher 10. As we discussed, so it is a new data set. Sorry, we discussed MNST data set. So it contains 60,000 color images. All of them are 32 cross 32 of size. Data set include 10 classes. So airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. Each class has 6,000 images. So this is a perfectly balanced data set, but the image size is very less. 32. So you, as you can see in this figure, image size is less. And we also small model. So this model will work on this data set. So to import this data set in the TensorFlow Keras library. So data and import this categorical. So first to import cipher.load the data set. So it will give X string, give string. So first we normalize the image basic processing steps, basic processing steps. Also, we split the validation data from the training data. We use 10% of training data as validation. So we multiply 0.1, 0.1 means 10%. So we extract this X validation and we make this data categorical. Okay, so as you can see, we have 45,000 images for training. Each image have 32 cross 32 cross 33, sorry, 3 size. For validation, we have 5,000 images. For testing, we have 10,000 images. So if you want to check the data set class distribution, so this is the class name. I make the array for class name to print. Then we can count. This is the simple code. You will know. Just print the data set. So as you can see in this bar diagram, this one data set is up, data equivalent. So now train the model on cipher train data set. So during the training, model will learn to extract hierarchical feature from index to convolutional layers, adjust weights using convolutional layers, using data propagations, and based on the convolutional layers, improves performance across your training and validation set. So it improves training model, just same model, dot fit model one and model one function for training. First, we have to insert the training data set. So, training data set is epoch. We are using 15 epoch. Base size is 64. For validation, Xwell and this Xwell watch. So we train this model. So up to 15 epoch, we receive this around 80% accuracy. So you can optimize this accuracy using hyperparameter tuning, which we discussed in previous notebook. So now we have to visualize these matrices. So just we compile model with lots of matrices. So you have to print the matrices. And just a simple code, how to plot a figure, plot, subplot, and plot history. History, as you can see, all the training is saved in this history.cipher10. So I assign is a new name history. So from history, you can extract accuracy, label it as train accuracy, and plot it. For validation accuracy, you can see the name of matrices here: accuracy, AUC1, precision 1, recall 1, validation accuracy, AUC, precision 1. You can check the name from there. You can see and you will receive this training and validation matrices plots. So as you can see, these are plots for accuracy, precision, recall, AUC, recall, AUC. Now, evaluating the model. For this, we are using the revision matrix function for best. We are using these matrices, and then you have to print that value. So we are getting a 68% test accuracy, and these are the metrics for testing. So next is confusion matrix. So as we know, it will give how many images are correctly classified. So this is the confusion matrix. For that, we import this confusion matrix function. So why predict probability we predict the X text, all the images of test set from this, and then we compare with true value, which because we have labels for all the value, and for confusion matrix, we plot this by y true classes and y predicted classes. How many classes which are correctly predicted, wrongly predicted, or images of class 1 and we predicted class 5. So so next one is classification report. For this simple from sklearn.matrices classification report, and first year predicted class, true class. Okay, so you will get this classification report. It will give for each class, for airplane class, you have 74%. So it will 4%. These decision is equal and F1 is good, you can find here in classification report. Now we want to insert some random images in the model, and we want to check its prediction. So for that, we take a random sample from the test data and insert in the model. Okay. So it will gives like this. So this is a image of cat, but model predicted as dog. This is image of cat and correctly predicted as cat. This is airplane and correctly predicted as aeroplane. Similarly, aeroplane, automobile. This one horse and we get horse, automobile like this. So this one is a truck, but model predicted as automobile, dog, and predicted as cat. So this model is not perfect. So how to tune the model to filter in? So what can we do here in this model? We did not imply many things in here. We want to tune what we imply here. As you can see, we are using we attitude but also another value for neurons. The value for neurons code. So I made this code. So similar import these matrices, this data set. So these matrices I want to show here. Okay. So this is the model. Instead of number of filter, insert number of filters. And in next layer we have to pass two times the filter. It means 32 means 34. So I filter 32 into number of filters. So my parameter is 32, 34, 64. I'm using base size also as parameter 32, 64. For epoch, I'm using 5 only. You can use another thing also. Using grid search, you can imply random search and Bayesian optimization, other things. Simple grid search, model name, parameter, we are scoring accuracy and fit the model, and it will give the best possible values of this function. I didn't include the result of this code because I want to use it as your practice. So train this and find the best possible matrices and hyperparameter for this model. So you can run this code. This will run. I checked this code. You can run this. So okay. So okay, we want to make a more complex CNN model. Let's say we want to use some residual connection, or you can say skip connection. So as you can see in this model, so it explains how skip connection works. So fx is let's say ReLU applied on x. We have x, then we apply ReLU, so we get f of x. For skip connection, we are using previous value xn minus 1 with this f of xn. We want to merge them. What it will do? Uh, it will prevent information loss. Because if the nth layer failed to learn the useful feature, the residual part still remain the previous layer. So in next layer, if we downsample the features, all the features, we have nothing. But if we use residual connection, we still have previous features because we add them to these features. Also, it improves gradient flow. Uh, Also, imply identity mapping, boost performance. So, uh, so this is the code for ResNet 18. So first we define the ResNet block. So just same. I'm using different method to define the model in here. In previous, I used different sequential method. This is the class and definition method. So so I want to teach you to different methods to define a model. So same thing we are using. So I want to just just take. So look here. So we are getting this from previous layer. These are the samples, but we are inserting merging next previous feature. So this is the residual addition. So this is the residual block. This residual block. This is the simple code. These are convolutional layer, and we at last we merge them. So to define this, we imply ResNet block of 66, 60, then 128, 128 block equals the number of neurons. As I say, it will double, so 64, then 128, then 256, then 512. Then global average splitting, then submix. Okay, so you can see in this is the code. So uh, you can train this model. I can show the results for this model. So I train in different notebook, same to same model. So this is the model summary. How many parameter? In previous model, we are having only, I think, 1,67,000 parameter. Now we are having, how many? I think 1 crore 11 lakh 96,000 something. So this much of parameter. So it means it is a more complex model. So it will give good results. Then same model compilation, as we all discussed, model compilation. In this, I use augmentations. What augmentations? One augmentations for a flip. So I want to read another method. So I use this augmentations. It is horizontal and right shift. These three and I will uh, length of friend said you discriminate this, you can choose other also. It means base size also. Base size is 256, same thing. So we done this model. So up to 54, we get 96. Same data. Data set is same, cipher 10. Same data, different model. So 96.58. Then similarly, we plot the training. So as you can see, we are having difference in validation and training matrices. So we can further optimize its learning rate, different combination of optimizers. You can use hyperparameter tuning, which we discussed in previous notebook, and you can optimize this model. I want to just teach you how to train and see the model and its training testing. So then test model dot evolute, then we get 73% test accuracy in we are getting 69, I think. So it is improving for confusion matrix. Also, you can say it is improved confusion matrix for classification report. So this is 73% accuracy. For predict, you can see the horse, automobile, frogs. One is deer, but it predicted is bird. Another is dog, it predicted is automobile. Another is cat, it predicted is frog. Truck, ship. So it predict less incorrect images. So I didn't include results of this modeling main file so that you can train the model. So also you can include train all different in compiling stage like this here. You can take different optimizers. I am using activation function here. So you can choose different optimizer activation function here. And also you can use a hyperparameter tuning. It is for your practice. Okay, so this is the for residual connection model. Next, we want to do image segmentation. So for image segmentation, there is model called UNIT. So we make a unit architecture for Oxford triple IT paid data set. So for unit path, we have unit is widely used architecture for image segmentation task. For biomedical and other also, it has encoder path, which captures context and extract the hierarchical feature using repeated convolution and max pooling layers. And this bottleneck layer, bottleneck means so it is like a U-shape model. So that's why we say it is a unit architecture. Bottleneck layer represents the compressed high-level picture representing the representation of the input. Decoder path construct the segment type, use the segment type. Convolution which is the this makes it very unit. So we are extracting pictures and then concatenating them with this. So, okay, so first is these are unit block. One is a double convolutional block in which we have a convolutional layer with activation ReLU and kernel initializer is he normal. This is the kernel initializer. First, we create this downsample block. We use convolutional layer, max pooling. For upsampling, we are using convolutional transpose layer and concate with the down samples and same dropout, then double convolutional block. It is just like a reverse of this down sample. So for main unit architecture, just repeated, as I see, repeated convolutional max pooling, convolutional max pooling. which is nothing but downsample block. We define this downsample block here. Downsample block, we imply this 4 downsample block, then this bottleneck block, and then upsample. Yeah. We use a softmax function for output. So as you can see, for this, then this. Okay. So if we name this as U-Note model, you can print the summary of this model. So as you can see, how many parameters it has? It has I think 3 crore 45 lakhs 13,000 parameter. It is more complex model than previous. Okay, so next is Oxford reply pet dataset. So it is a dataset. It consists 73 category of pet images, including various breeds of cats, dog. Each image is annotated with class labels and pixel level segmentation masks like this. So for this image, this is the mask. This is the mask. So we extract this data set from Kaggle. Then data processing and resizing. We are resizing this image to 128 to 128. Also, we want to we also have to resize the mask also, segmentation mask. We resize both of them. Then we apply these two augmentations, one augmentations on random flip. Then we normalize the image. We divide it by 255, which is maximum pixel value in an image. And then we load the data set. To prepare the data set, one is training data set, one is testing data set. We prepare the data set, the simple code load the set, the simple code. So then 64 buffers 1000. We also have to make the validation bits. So it's validation base. These are simple code. They code. Okay, so then we display some sample. Then we display some from the data. So this will take the random image from the data set and show the marks. This is also simple code. That is discussed in previous. So this is the image. This is for dog, I think, and this is the mask for this image. Now we have to train the unit model. We are using ADAM optimizer U and only accuracy matrix. Number of epoch is 5. Training length is in previous code we divided. Now is load number of example. Same. This we use this early stopping, patience, weight restore. We can restore the best weight. This is strategy we use, and we train the model by dot fit. First is train batch, which is training data set. The number of epoch, step per epoch, we defined it in here. Step per epoch, train length divided by base size. Also, we did this thing in previous one. Also, validation data set and early stopping. So there you go. I imply 50 epoch, but it stopped after 4 epoch because validation accuracy, we are monitoring so it is improving from this point. So it will become now improving more from this point. So it gives predicted. This is the true mask. This is the predicted mask. As you can see, it has a lot of similarity. Overall, also this image true mask and predicted mask. For this image also, this is true and predicted mask for this also. So to save a model, there is command unit.save model. So this is unit model. You can save this model, and you don't have to train it again. You can insert the image; it will give the results. Okay. So if you have any questions, doubts, you can ask me. Hello. So you can write in it in the chat box if you have any questions. For CNN, this is the basic information how to train the model, how to how data sets, test training and validation. Like this, you can use any creative model with different number of neurons base size. Hello, sir. My session is over, so you can start.
So
You and Pooja can start, sir.
yes, so I'll just start sharing my screen. Okay, so now in this session, hello, am I audible?
Yes, sir, you are audible.
Okay. So now what we'll do next today is like we have understood recurrent neural network in the theory class, theory lecture in the morning, and what we have planned, me and Pooja, that we will first start with the basic implementation of recurrent neural network for word prediction problem. I will show you a very simple implementation of recurrent neural network for word prediction problem, and I will show a very small code how we can write the recurrent neural network using Keras library. Okay, and using with the functional API method, and then I will also show you code in which we can also visualize the embeddings and the what is the internals is being learned on the recurrent neural network. With the very small recurrent neural network, we'll see how the weights are updated, and then how with the different timestamp, how the units are being updated. Like we have seen in a recurrent neural network that when we move from one timestamp to another, so weights will be shared, and we'll observe that okay, it is like on timestamp 1, and then we move to timestamp 2, we'll see the values of the hidden values. Okay, and then that will give us the idea that okay, this is weights are shared, and then that will give a better idea and understanding of the recurrent neural network. And then we'll also see implementation on time series problem using recurrent neural network, and sentiment analysis problem using recurrent neural network. This is all what we are going to do. And let's start. Okay, so this is first implementation of recurrent neural network, in which I just installed TensorFlow and Matplot lib library for that using the functions and the inbuilt functions of these libraries. Okay, and these are the imports which I have taken, and mostly I've used Keras. In the Keras, there are two ways we can implement any sequential models. One is the simple sequential model, and second is using the functional API method. So if you have more than two inputs and you do not have that sequential way of training the model, then you can use some functional API based method. So in that case, we use model. Okay, and then we have different layers which we can define, like input layer, embedding layer, then we have a simple RNN, and then dense. Okay, and then Keras also provides pre-processing methods for tokenizer and converting the values to the categorical and padding the sequences and all. Okay, so just start. Let's start with a very small, like toy corpus, which I have taken 5 sentences, and then we do the tokenization. Okay, and then we generate the input sequences, in which we convert all the input sentences to the input words to the sequences, which we already seen many times in different lectures, and we convert. Give the like IDs, and then we also do the padding of the sentences to the maximum length. But here I've purposefully made this comment here. So you can see that in the lecture we have seen that in recurrent neural network there is no need to do the padding part. But here, why we have done the padding in the implementation is it's because that implementation, when we do the implementation, this padding is not for padding will not be fed into the network. But what we are doing is we are padding it just because we want to will be feeding all this data to the network in batches. So to just for the sake of the implementation part, we are doing it. But when will the model when model will be trained, it will not consider the padding sequences. It will just stop whenever there is no further words. Okay. So that is why we are doing it. So don't confuse this with the concepts which we have discussed in the morning session, where we were saying that padding is not required in recurrent neural network. So that is why I just purposefully taken this example. Okay, and then all the input sentences are stored in variables. X is for the input data, Y is for the labels, and then those are transformed to the categories. Okay, and now see this is the model in which we start with the input layer, and we define it is like this. And after this function, we have to give the size of the input layer, and then we have embedding layer. Embedding layer is having two important parameters. First is the total vocab size, and the second is the embedding size. So for this toy model, we have used very small embedding size of 10, and then we should connect it with the previous layer. So here we give the name of the previous layer. So for the embedding layer, the input is the the embedding layer will take the input from the input layer, and it will, the name of the embedding layer is, let's say, embed. Okay, now if you remember, so first layer is embedding layer. So all the inputs are converted to the embeddings, and then they are connected to the simple RNN function network layer, in which it is connected with the embedding layer like this. And then this recurrent neural network has mostly important two parameters. One is 32. 32 is number of hidden nodes. If you remember, the number of nodes in the hidden layer nodes is hidden layer is like in each intermediate, that hidden node, it will have 32 nodes, and which will be fully connected with all the embedding input values. Okay. And then we have a parameter return sequences, which is now false, because for this example, if you remember that recurrent neural network, we have many to one mapping. So we don't want to have intermediate outputs, because we are just interested in, given the sequence of words, we just want to predict the next word. So we are only interested in the last output. Okay. So that is why we have made it this as a false. If you are interested in, like, for example, part of speech problem, or character prediction problem, or any other problem which requires to take care of all the output of each timestamp, then we make it as a true. Okay. And then finally we have a dense layer, which is like have two parameters again. So first is the total number of class values. For this, we just want to map like from the vocab what should be the next word. And then we have a activation function as a softmax, because it is a multiple class problem. So we have softmax function, and this dense layer is connected with the output of the recurrent neural network. Okay. And that gives us the final output layer. And we create a model by giving the input and output. This model will automatically create the network itself based on its implementation. Okay, so this model has been defined. Next, we compile it with the cross entropy loss function and Adam optimizer, and we are using accuracy for measuring the metric. We can then see the model summary, which we'll just see. Okay. And then we've used the fit function for training purpose, and then we just plot the loss, and this is a function which we can use to predict the next word. Okay. And I'm just printing for some sample examples, and then we also visualizing what we see on the hidden layer. So this is all about the code. Now I'll just run and let's see how it works. Okay, so let's say this is the architecture, which shows like input size is 3, embedding dimension is 10. Then we have 32 nodes in the recurrent neural network, and then 10 is total vocab size, that is total word size. Okay. So I just taken this small example just to give you an idea that how you can use functional API to implement the recurrent neural network. So for the words I love, it predicts the next word should be machine based on the training which we have used and the TIA data which we have given. And now you can also see that this is the final recurrent neural network hidden state, which we can visualize. And by this, you can understand that, okay, so there are different variation in the output. So it means that that the final node is basically quite sensitive to the different inputs, and it is somehow learning somewhat some information based on the inputs, and it is changing by giving the different inputs. Okay, and now let's run this code and try different other words also. So if I write machine in the input, so it will just a second. Okay, I just deleted one function here, but anyway, this is just an interactive way of running the same function, which we have already seen. We can try with the different other functions. Let's say I just try some other function. Some other input, let's say I write machine here. So let's see what we get as an output. I have to take this one. Let's say I write machine. So next word is predicted learning, and you can see that the model is being learned somehow. Now let's say I write machine learning as an input. So it will now predicting next word as is, which is quite good as per our training data. Now I write, let's say input is machine learning is. Now it is predicting next word to be fun. Okay. So the I plan for this small notebook is to give you an idea that how you can easily use it. Just take your data, create your own uh, create your own network, make it more complex, and then train it based on your problem. Okay. Now we'll just quickly see another small script in which I just wanted to show you how the hidden states changes from different inputs. So I purposefully made this script to be very small, and you can see that how you can easily implement also. Uh, just Okay, so this is a recurrent neural network in which we created our own. So in this script, we are creating our own functions instead of using Kera's implementation of recurrent neural network. Okay, so in this, you can just see that this is the implementation of the class recurrent neural network in which we have two weight matrices which we know about it. So Wx is for weight, storing the weights between the input and the hidden nodes, and Wh is a weight matrix which will store the weights between hidden to hidden layers. Okay, so this is, and then we are using 10H as an activation function at the hidden layer. And then this wraps all the functions which we have defined. Okay, so you can just give the best size timestamp and then inputs. So based on that, it will just run. And now I just show you, and you can just pass the number of hidden units. Okay, so let's see what we see when we run this script. So in this, we have only two nodes, two timestamps and two nodes. Okay. So you see that this is the first graph is showing the activation values at hidden state or of first timestamp. Okay, so you see that the values is changing somehow. It is not making any sense, but what you can observe here is when you see the output at activation values at timestamp T1, oh sorry, T2. So after T1, the change which you are seeing is same as you have seen on the timestamp 1. So when the values of timestamp is changing, so let's say we are at timestamp 2, T is equal to 2. So the values which you are seeing is basically changing like it is big, weights are being shared. So that is that this graph shows that the values which we are updating with the different timestamps, it is also being updated with that. Okay. And again, I just run this for the sentences, and then we'll see that what is the embedding values which we see on the change in the embedding values during the training process. Okay. So now the code is almost same, just the only difference is we are giving different words now. Now you can see that when we are at timestamp t is equal to 1, and this is the hidden state over the time of different words, and this is at timestamp 2. Okay, and you can observe that the values for unit 0 is basically similar for each word. So now we'll talk about recurrent neural network for for time series forecasting problem. And now that Pooja, I request Pooja to explain the code for this.
Yes, sir.
Now I'll stop sharing and then you can.
So, sir, is my screen visible?
Yes.
Okay, sir. So, welcome participants. Welcome to the hands-on session of RNN for time series forecasting problem. Basically, in this notebook, what we will do is we will use RNN model to predict the temperature given a series of temperature. For in this notebook, we will give 10 days, continuous 10 days temperature to our RNN model, and then we will predict the 11th day temperature by RNN. So for this, we use MEL, that daily minimum data set which consists of here one which corresponding minimum temperature of the day in degrees Celsius. So like in the last code, we the data set consists of we import a library and import library. Library. So in this code, we will from the what will import the data file if the data file is stored in your computer. So it's from the data directly or data library. We will learn how to import the data from the data and the data set file is stored in your computer. So let us start with the code. So we start first by importing all the necessary libraries. We import pandas as PD, we import numpy as np, matplotlib as plt, sklearn processing. From there we import min-max scalar function. From sklearn.model selection, we import train test split. These are the required libraries that we will be using during the code. So before starting with the any coding process, we will need to clean and pre-process our data set. Like if our data set is containing some bad entries, so first we need to remove it. Then we start with the coding process. So here the dataset file is named as temperature.csv. So how to import this file in Google Colab Notebook? So file from here when dataset type in temperature. Here we dataset type the CSV file, which is our dataset file, which contains that data. Temperature. So this is how the data looks like. I have printed some entries. So the data set is the data set is 1990. The minimum temperature of that day is 13.4 degrees Celsius. On 16 December 1990, the minimum temperature is 13.6 degrees Celsius and so this is how our data set look like. So now what we do is we start by pre-processing the data before starting with the coding part. So here first we have imported our dataset file. Now here we have removed all the bed lines of the dataset. Like if there is any bed line, so first we have printed all the bed lines if we can find. Then we have removed those bed entries or bed line. What should I say? Bed lines from our data set to make our data set clean. So this is how, like, when we printed the backed entries of our data set, so on the 565th row, that is on 20th July of 1882, the data says the minimum temperature is recorded like this, which has no meaning for a computer, as it is it include a question mark, so which has no meaning. Similarly, there are another two entries for which the temperature is also reported as question mark 0.8, question mark 0.1. So after removing these kind of entries, we see our dataset file, and after clearing the dataset, now we will start the process. So what we are doing here, we take a input of 10 days temperature to our output. We try to predict the 11th day temperature depending by running a model with the sufficient amount of data. Then first import the min-max scalar. What this min-max scalar function do is, as the range of our data, the minimum temperature varies. Let us say the minimum range of the temperature is vary from 10 to 25. So this min-max scalar function is doing what? It is transfer. It is transferring the complete range to another range that is -1 to 1. Why we are doing this? We are doing this just to fast our training process. So we are scaling the total range of by increase, so within -1 and 1 range. We define the sequence length, that is we are 10. That is we are importing or we are giving 10 continuous days minimum
Pooja?
temperature.
Hello.
Start by defining the input and output. Yes, ma'am.
Hello.
Yes, ma'am.
Pooja, your voice is not at all
Hello.
clear. Your voice is not at all clear. There is a lot of audio and video issues, screen issues. So what we can do is, since this is the another application of recurrent neural network, so we will share this notebook with everyone. They can run it on this, because there is, I think, technical problem here in the network. When Sir was taking the session, his session was clear, because because of the internet issue here, we are facing difficulty. Am I audible?
Yes, ma'am, you are audible.
Yes.
Yeah, so this is creating a lot of issue for conducting the session. Technical issues is there. So because this is just another application of recurrent neural network, what we can do is we can just share this code file with everyone, and uh, and give them to time to run it on their own, and then we can take up questions, if any, in the chat box. Okay, rather than explaining this code, because it is not at all clear. There is no point in explaining it this way, because it's not at all clear. A lot of technical issues are coming. The voice is breaking all the time. So we will
Okay, ma'am.
upload this code file in the canvas. We will upload this code file in the canvas, all the code files which the sir has taken, and this one also, so that you all can run it on your own. And if there are any issues, we can just take it up in tomorrow's session, or even in WhatsApp you can contact. Okay. So I think we can meet tomorrow now. We can resume tomorrow at 9 a.m. Yes.